everyone. So today we're going to have a new topic on Bim columns. Okay, so Bim columns are structural members subjected to combined axial compression and flexural loading. Again, these are called beam columns. So basically, it serves as a beam. At the same time, it also serves like as a column. Okay, so when we say beams, these are structural members that carries transverse load, meaning the loads are applied perpendicular to the axis of the member. While columns are compression members that resist axial compression. Okay, so when these two types of loads are being induced in the member, so the member would be considered or analyzed as beam columns. So as you can see from this figure, we have here examples of beam columns. On the left side, you have there the beams and columns on a frame. Okay, so the whole frame consists of beam columns. So basically, the first level of this structure or of the frame has a cross bracing or a lateral support. So that means that the first level of the frame is considered as a frame without side sway. However, on the second level, as you can see, there is no lateral support or cross bracing attached on the frame. So for this case, due to that lateral load P sub 1, it could experience side sway. Okay, so when we analyze the columns here, so the columns would be experiencing moments that makes it as a beam. At the same time, due to the gravity loads, the columns will experience axial compression. Thus, the columns on this particular frame are considered as beam columns. Likewise, the beams, let's say the beam AB and the beam CD, due to the uniform load, transverse or gravity load that it carries, they experiences or they acts like a beam. However, because of the presence of P1 and P2, which are lateral loads, and these lateral loads induce axial compression on the beams as well. Therefore, beams A, B, and CD are also considered and it must be designed as beam columns. Okay, so basically, columns and beams in especially on a moment resisting frame, are considered as beam column. Another example that you can see from this figure is on the right side, wherein we have a top chord with transverse load coming from the purlin support reaction. So this is possible for the top chord whenever the top chord carries a purlin which is applied at the not at the joint. Let's say for this one in the encircled figure, so we have a purlin placed at the middle of the top chord. So if we're going to analyze this top chord over here, okay, so due to the presence of the purlin on this point, so the top chord experiences bending. No, although we know the fact that in analyzing truss members, we only considered axial forces. So basically, for top chord, it carries axial compression. But because of the presence of this purlin on top of the top chord, so the top chord, aside from axial compression, it also experiences bending. So therefore, for this particular case, that this top chord member is considered as beam column. So if you want your top chords to be analyzed as actually loaded members, in the analysis, you do not place purlins at the mid span or within the span of the top chord. So it would be easier or practical to place all the purlins at the joints of the top chords. Okay, so in these cases, we have to analyze these members as beam columns. Now, my question is, how do we analyze? Now, how do we analyze? How do we design such beam column members? Okay, so we have this LRFD interaction equations that we need to follow. So we have two cases. Number one is if this ratio PU over phi PN is greater than or equal to 20%, so the member is considered as or experiencing larger axial compression. Larger axial compression, that means the member is more of a compression member. Okay? So, since it experiences larger axial compression, this would be the interaction equation that we need to satisfy, such that the Pn over Vpn, or rather Pu over Vpn, okay, plus 8 over 9 of the Mux over Vmnx plus Muy over Vmny should be less than or equal to 1 for adequacy. So as you can see from this interaction equation, okay, so from this interaction equation, that the equation is more of compression, this one. No? So this item is more of axial compression. 8 over 9, so 8 over 9 only is allotted for bending. Okay? So while for the second condition is this is applicable whenever we have Pu over Vpn less than or equal to 0.2. Okay? So ibig sabihin, mababa, okay, mababa yung contribution ng axial compression. So that's why it's named as smaller axial compression. Since smaller axial compression, basically we could consider this as more of a flexural member. So if you could see, look at the interaction equation, the equation involves more of flexure. Only half, because of this one half, is being considered in the axial compression. So the equation becomes P sub u over 2 phi Pn plus the Mux over phi Mnx plus Muy over phi Mny. Okay, so again, Pu is the ultimate load or the ultimate or the factored axial compressive force in the member. Okay, so this should be factored. Okay, now phi sub c is the resistance factor for compression, which is 0.9. And yung Pn is the nominal compressive strength. Okay, the nominal compressive strength of the member, and this is basically the FCR times the AG. AG is the gross area of the column section or of the member. Tapos yung FCR naman, if you could still recall, we have two equations for FCR. One is for the equation for intermediate column and the another equation FCR for long column. Intermediate and long column can be identified based from the its largest slenderness ratio compared with the critical slenderness ratio. So that is the Phi sub n. Now, how about for the bending component? So okay, so yung MUX, again, this is the factor or the ultimate moment on the beam. Okay, so on bending about x-axis. Okay, or the major axis. Tapos yung MUY naman is the factored. Okay, MUY naman is the factored moment caused on the beam based on the weaker axis or the y-axis. Tapos yung resistance factor naman natin for bending, as we know, it's 0.9. Tapos yung MUX, okay, yung MUX naman, paano kinukuha yung MUX? Ito yung medyo maraming equations involved in identifying MUX, wherein you have to check for the compactness, di ba? So compactness of the section, the lateral support condition, tapos yung ano pa, yung C sub B, no? So yung C sub B value. Okay? So tapos yung MUY naman is a much simpler. Yung MUY is basically dependent on the compactness of the section lang. Okay, so from here you could have the equation for MUX. Pagka fully supported, MUX is just FYZX, diba? Tapos kapag partially or unsupported yung member natin, so we have corresponding MUX equations wherein that MUX should be always, you have to check with the limit with the MP. Okay, tapos yung sa MUY naman, ganun din, no? So kapag compact yung section, yung MUY natin is just FYZY. Otherwise, kapag non-compact, we have a different equation for MUY naman. Okay? So basically, lahat ng mga variables or parameters used in these interaction equations for beam columns are already discussed in the previous lectures. Okay, so basically it's a combination of course outcome 2, which is the compression member, and at the same time yung sa flexural members. Okay, So that is how we analyze beam columns based from the two LRFD interaction equations. Now, let us have this first sample problem using those interaction equations or formulas. So I think this is a very similar with the problem given in the actual board exam. So we're given with the beam column shown in the figure. And as you can see, the beam column is hinged at both ends, top and bottom, and it is subjected to the loads shown. So as you can see, we have an axial compression applied at the top, which is 155 dead load and 440 live load. And these are service loads. Then at the same time, at the mid-span, to 5.2 meters the full span of the member. At the mid-span, there is a lateral load, Q. Okay, so Q dead load is 22 kilonewtons and the Q live load is 53 kilonewtons naman. Okay, so the member is W10 by 49, 8992 steel is being used. Okay, so the properties of the W10 by 49 were shown in the table so below, so which was taken from the steel manual. And at the same time, for A992 steel, its Fy is equivalent to 345 megapascal and its Fu is 448.5 megapascal as given in the problem. It is also stated in the problem that we assume compact section. Therefore, we don't need to check the compactness of the given section. So we are asked to determine whether this member satisfy the appropriate AISC specification interaction equation, meaning is it really safe? No, so we have to check it against with the interaction equations that we had earlier. Then also it is stated in the problem, do not consider moment amplification due to effects of secondary moments, which is the P delta moments and the P delta moments, or the capital and the small delta moments. Because if we consider those P delta effects, there will be a magnification of the moments on the beam column. Okay? Okay? So for the solution, basta whenever you encountered such problem na beam column, like for this example, 'di ba? We are convinced that the member is a beam column, okay? Because due to the presence of the axial compressive load, so that makes it as a column. And due to the lateral load, okay? So the Q loads, that makes it as a beam. Okay? So whenever we have member resisting to axial compression and bending or transverse load, it would be considered as beam columns. Then for beam columns, the first step that we have to check is kung smaller or larger compression ba siya, axial compression. How? We have to check with this PU over VPN compared with 20% or 0.2. Okay. So what is PU? PU is the ultimate or the factored axial load, axial compression, axial compressive forces, which would be coming from the 155 and the 444. So making it factored, so multiplying with the load factors, we got 890 kilonewtons. Okay, so then how about the design strength for compression, the PN? Okay, so for the PN, for the nominal compressive strength, it's basically FCR AG. So how do we do that? So we have to check first for the largest slenderness ratio of the member, KL over R. K is 1 since both ends are hinged, length is 5.2 meters, and the R is the minimum radius of gyration. For this case, since no lateral support is being provided on the column, therefore the R minimum would correspond to the RY. So that RY of 64.52 was taken from the table steel manual. So we got 80.595 to be the largest slenderness ratio of this member. So we have to compare it with the C sub C. So C sub C is 4.71 square root of E over Fy. So we got 113. So as you can see, our slenderness ratio 80 is less than the CC 113. Therefore, we have an intermediate column. For intermediate column, FCR is given as 0.658 raised to Fy over Fe times Fy. Ano yung Fe? Fe is the Euler's critical stress. So using the equation, pi square E over the slenderness ratio maximum square, so we got 303 megapascals. Okay, so substituting that F sub E in the FCR equation, so we got FCR to be 214.512 megapascals. Okay, so having that FCR, multiplying it with the gross area of the section is 929290. So we got P sub n to be 1992.821 kilonewtons. Okay, so therefore, so checking the ratio of the PU over VPN, P is 0.9 for compression. So we arrive with this ratio of 0.496, which is of course greater than 0.2. Therefore, the member is considered as larger axial compression. Okay, so larger axial na. So what would be the interaction equation that we need to satisfy? So remember, pagka larger axial, it's more of axial. So if it is more of axial, 8/9 of the moment lang ang i-consider mo. So that would be the interaction equation, yung 8/9. Ayun. So that would be the interaction that we need to satisfy. So yung first term, yung PU over VPN, tapos na tayo dyan, no? So 0.4 na yung sagot natin dyan. So okay na yan. So di bali dito na lang tayo sa moment. Basically, the moment about y is 0 kasi it was given in the problem that the transverse lateral load was applied to resist the stronger axis or the major axis. So therefore, wala tayong bending about the minor axis. Kaya yung MYX natin is just equal to 0. Okay. So ano yung MUX? Yung MUX would be the maximum moment based from the factored load. So as you can see, diba, hinge at saka hinge sa taas. So para mo siyang, i-consider mo siya as beam, pagka tinignan mo siya na nakahiga, parang simple beam na may concentrated load sa midspan. Yung concentrated load sa midspan, yun yung Q na load. O, anong maximum moment for a simple beam with the concentrated load at the midspan? Anong maximum moment? Diba yun yung PL over 4? Okay, so I just compute first for the factored load due to the lateral load, 1.2 of the dead plus 1.6 of the live. So we got 111.2 kilonewton. So yan yung pinaka-lateral load, factored load. Then yun nga, yung Q natin would be the concentrated load applied at the midspan, so of a simple beam. So parang ang maximum moment natin dyan is PL over 4. Di ba? So PL over 4, yung P yun yung Q, U. QUL over 4. So naging MUX natin would be 144.56 kilonewton meter. So yun na yung MUX. Now, next would be ano yung MNX or the design phi MNX, the design flexural strength. Okay, so ito naman yung sa previous discussion natin for flexure, 'di ba? So we have to, since yung compactness hindi na natin kailangan gawin since the problem gives us that the section is already compact. So we will start with the checking of the lateral support condition. So how do we check lateral support condition? We identify the L sub B. The L sub B is the unsupported length, which is 5.2 meters. Then we compare this L sub B with the L sub P tsaka sa L sub R, if you could still remember, no? So yung L sub P, so yan yung 1.76 Ry square root of E over Fy. So we got 2.7 meters. So 2.7 meters. So ibig sabihin yung LB natin, 5.2, mas mahaba siya kaysa dun sa LP. So ibig sabihin nun, hindi na siya laterally supported. So pwede siya maging partial, pwede rin siyang unsupported. So we have to check the L sub R limit. Okay, for the L sub R limit, so we have to use, or we will be needing the RTS or yung special radius of gyration, tapos yung torsional constant J. Okay, so I solved for that RTS and J. So I didn't show it here na lang. And solve for the L sub R to be 14.7 meters. 14.7 meters. So ibig sabihin yung LB natin na 5.2 is less than naman dun sa LR limit para siya maging unsupported. So basically nasa gitna siya ng LP at saka ng LR, meaning it's partially supported. Now, pagka partially supported yung beam, ano yung yung MNX natin? So, diba may equation tayo dyan. So, as per the NSCP code 2015, so that would be the MNX equation, so involving the MP and the CB. So, I solved for the MP. MP is the plastic moment, which is Fy ZX. No? So, we got 341. So, Fy is 345, yung ZX section property taken from the steel manual. Tapos, I solve for CB. Okay, ano yung CB? Since this is para siyang hinge at both ends naman, tapos may concentrated load sa gitna, so para siyang simple beam with concentrated load sa gitna. And we have derived this already. That CB is equal to 1.32. Ayan. So when we substitute CB, MP, LB, LP, LR dun sa MNX equation, we will arrive with the MNX value of 416.9775 kilonewton meter. And if you will notice, yung calculated MNX exceeds the limit of 341 na MP. So therefore, for this case, we will be adopting MNX equals MP. So yun yung MNX natin equals MP. So back substituting all the equations in the interaction equation for beam column. So substitute it all. So again, yung first term, yung P over VPN, nasolve na natin yan kanina from the previous slide. So that is 0.496 plus 8 over 9 of MUX. So MUX is here, 144. Tapos divided by phi MNX. Okay, so yung phi natin again is for flexure, it's 0.9. Tapos yung MNX natin is equal to MNP or plastic moment. And check whether the interaction equation value is less than or equal to 1. And calculating for the value, so we got 0.914. 0.914 is less than 1, therefore, it is safe. No? So the chosen section for this beam column is actually safe. So if you will notice, the value of the interaction equation is 0.914. Medyo malapit na siya sa 1. So ibig sabihin, we can consider that the chosen section is also economical choice. Okay, so or you could also try try checking yung mas mababa, no, mas mababa yung weight with this chosen section na kung saan it could give you an interaction equation value of mas malapit sa 1. Kung kaya mong mapalabas yung 0.999 something or eksakto 1.0000, so that would be the most economical section and safe for this type of loadings. Okay, so that would be an example of analyzing beam columns based from the interaction equation that we have. No, okay. So again, for this interaction equation, for this solution, the problem falls under larger axial, no? Mas malaki yung contribution ng axial compression. So the second possible example for this type of problem would be yung ano naman, maging smaller axial. Pagka naging smaller axial naman, iba lang yung interaction equation that you have to use to check for the adequacy of the member. Okay, so that's it. So I hope you have learned out of this simple example on beam columns. Thank you.